This video is 4.3, connecting f prime and f double prime with the graph of f. Some of this I'm going to fly through because it's kind of like we've already done it, and then some of it I'm going to have to slow down and really emphasize. It says, given the graph of f, label the relative extrema. Well, it would help if I didn't have a pen. That's a max, and that's a min. Okay. It says, sketch f prime as accurately as you can below. Label the x values of the extrema from f and f prime. Well, the graph is increasing, so it's positive here, negative, positive. And you have zeros, horizontal tangent lines, at wherever that is. Let's just kind of drop it down. It's about 1 point, I don't know, 2, and then, let's see, is that straight? Are those even lined up? No. Gosh. Let me see. That's 1, 2, 3, 4, almost 5. So 1, 2, 3, 4, almost 5. And it's above the x-axis, below, above. So it's going to be above, below, and above. And that should make sense. And then we have, whoa, there was more to that. We have this, check number 1 and 2 in the box below with the graph you just checked. If f prime changes from positive to negative at c, then f has a local maximum value at c. And we should already know that. If it changes from negative to positive, then it's a min. And if it does not change signs, there is no local extrema. Remember that if it's closed to interval, you must test the endpoints. It says find where the function h of x equals x times the square root of 4 minus x squared is increasing and decreasing. Then use the first derivative test to determine any local extrema. Well, that means we have to take the derivative. In this one, I'm going to rewrite it as x times 4 minus x squared to the 1/2, and we have to use the product rule. So 1 d2 minus x squared to the negative 1/2 times negative 2x plus 2 d1. Okay, and this part, the 2 and the 2 cancel out, and we wind up with x times x, which is x squared, over the square root of 4 minus x squared, and it is negative because there's a negative sign, plus the square root of 4 minus x squared. You're going to have to get a common denominator, which would be the square root of 4 minus x squared. If you have to multiply it on the bottom, you got to multiply it on the top. So this one did not change. The square root of 4 minus x squared times the square root of 4 minus x squared is the square root squared, which is just 4 minus x squared. Then we can combine like terms on the top. That's going to be 4 minus 2x squared over the square root of 4 minus x squared. Remember that the critical points are where the derivative is equal to 0 and where the derivative is undefined. So 2x squared equals 4, x squared equals 2, x equals plus or minus the square root of 2, and then we have x squared is not equal to 4, so x is not equal to plus or minus 2. Okay, so on our sine graph, we have negative 2, negative square root of 2, positive square root of 2, and 2. And if we look at our original function, we can't keep going because if you look at the domain of the original function, remember that you can't take the square root of a negative number, so you would have to say 4 minus x squared has to be greater than or equal to 0. So that's the same thing as saying x squared is less than or equal to 4. That's a conjunction, so it's between. You get plus or minus 2, so it's between negative 2 and 2. If you don't believe me there, do a sine graph, and that's what you get when you do your sine graph. I'm just trying to save time on the video for actually solving this. So this function stops. at 2 and negative 2. Negative 2. The graph does not go any farther than that. It's boxed in. Okay, and then we have the square root of 4 minus x squared and 4 minus 2x squared. We test points. On this interval, this piece is always positive. And then 4 minus 2x squared, if we plug in numbers, negative 1.5 would work. You're going to get a negative. And then 0, you're going to get a positive. And then 1.5, you're going to get a negative. So you end up with negative, positive, negative. So h of x is increasing between the negative square root of 2 and the square root of 2 because h prime of x is greater than 0. H of x is decreasing from negative 2 to the negative square root of 2 and from the square root of 2 to 2 because h prime of x is less than 0. And if you kind of do like that, it has a max, a relative max at x equals negative square root of 2 because the derivative changes from, wait, that's just min. I don't know why I wrote max. I was just kidding. Min. H prime of x changes from negative to positive. Changes. And then a max at x equals the square root of 2 because h prime of x changes from positive to negative. Let's see. And I should really plug it back in to the original and get the y values. If we plug that back into the original, we're going to get, let's see, I plug in negative square root of 2 right here. Have I not already done this on my paper? No, I didn't. Really? That's horrible of me. I really should. At negative square root of 2, let's see, I will get negative square root of 2 times 4 minus negative square root of 2 squared. 4 minus the square root of 2 squared would be 2. 4 minus 2 is 2, so negative square root of 2 times the square root of 2. So how about negative 2? So y equals negative 2. And then if I fill in a positive square root of 2, I'm going to get the same thing, but it's going to be a positive 2. Y equals 2. So that's the max, and that's the min. Whew, that was long. Find where the function g of x equals x squared times e to the x is increasing and decreasing, then find any local extrema and absolute extrema. Again, we have a product rule. So g prime of x equals 1 d2 plus 2 d1. I've got to set this equal to 0 now. So I've got x squared e to the x plus 2x e to the x equals 0. Hey, I can factor out an e to the x and get x squared plus 2x. So 0 product property says e to the x equals 0. I can actually take out an x as well. X plus 2. So x equals 0, x plus 2 equals 0. So I get 3 answers. I get 0, I get negative 2, and then I get where e to the x is 0. If you look on the board over there, e to the x is Jacob. E to the x does this. It has an asymptote of my x-axis. It never equals 0, so I just basically throw it away. Okay. So I do my sine graph. I've got negative 2, and I've got 0. I have e to the x, x, and x plus 2. Note, e to the x is always positive. X changes sign at 0. X minus plus 2 changes sign at negative 2. So you get positive, negative, positive. So it's increasing g is increasing from negative infinity to negative 2, u 0 to infinity, because g prime of x is greater than 0. G is decreasing from negative 2 to 0, since g prime of x is less than 0. It has a max at negative 2, at x equals negative 2, since g prime changes from positive to negative. It has a min at x equals 0, since g prime changes from negative to positive. And then we would need to actually go in and find our y values. At negative 2, g of negative 2 equals negative 2 squared times e to the negative 2, which is 4 over e squared. So, comma, 4 over e squared. And then g of 0 is 0 squared times e to the 0, which is 0. So, 0. Just ignore the x equals. Let's see. Concavity, yay, the second derivative. Concavity deals with how a graph is curved. A graph that is concave up looks like a bowl that you could put cereal in, while a graph that is concave down looks like a bowl that the cereal would fall out of. Here's your Cheerios and your milk all falling out. We can use the second derivative to determine the concavity of a function. The second derivative is where concavity comes from. The graph is concave up if f prime is increasing, and concave down if f prime is decreasing. It says if the first derivative is increasing, then the second derivative must be positive. If the first derivative is decreasing, the second derivative must be negative. Thus, instead of using the definition of concavity to determine whether the function is concave up or down, we can use the following test. It's called the second derivative test. It says the graph of a twice differentiable function is concave up if the second derivative, y double prime, is greater than 0, and concave down if it's less than 0. And here's a stupid way to remember it. Concave up plus happy face, concave down minus sad face. So if the second derivative is positive, it's concave up, negative, concave down. Am I getting ahead of myself? Please note that while this is a humorous and hopefully helpful way to remember concavity, please understand that it's never to be used as a justification on any test. If you are taking the AP test and you're finding the second derivative and you're finding where it's concave up, and as your justification you put plus smiley face, you're not going to get credit for that. You need to say because the second derivative is greater than 0. It says using the same graph as our previous example, indicate which portions of the graph are concave up, which portions are concave down. Label the graph where it changes concavity. Well, here is concave down because your cereal would fall out. On this part, it's concave up. So this is up, this is down. The point where it changes concavity is called a point of inflection. You think about x cubed, our classic, it's our muscle man. Right here, concave up, concave down. And remind me in class tomorrow to talk about the bowls. Like here's the candy bowl up, it's red. Here's the candy bowl down. If I put them together, the place where they meet, right there, is the inflection point. Concave up, concave down. The graph of f prime is graphed below. Label the x value where the graph changes concavity. Verify this with the definition of concavity as it relates to the first derivative. This is where it gets tricky. This is f prime. Okay, What is the definition of concavity? F is concave up if f prime of x is increasing, which means f double prime of x is greater than 0. It's concave down if f prime is decreasing, or if f double prime is less than 0. So again, this is f prime of x. We're looking for where f prime of x is increasing. That's where f prime of x is increasing. And where is it decreasing? So where does it change concavity? It changes concavity at the minimum on this graph of f prime of x. So that's where the inflection points. Inflection points are the maxes and mins of the first derivative. Sketch the graph of f double prime. On the graph below, label the x value where the graph changes concavity. Verify this with the definition of concavity as it relates to the second derivative. Note that it is decreasing, so it's going to be below the x-axis, and then it's increasing, so it's going to be above the x-axis. So, and remember the equation of the derivative of a parabola is a line. So the minimum was at 3, so it's below the x-axis, it's above the x-axis. So this is where the second derivative is 0. So, and verify this with the definition of concavity as it relates to the second derivative. F is concave up if f double prime is greater than 0. F is concave down if f double prime is less than 0. Find the intervals where the function I might have to stop this video and split this up into two different things. We'll stop after this example and we'll finish the rest tomorrow. Find the intervals where the function is concave up and concave down. Well, you take a derivative, you get negative 2 times 3 is negative 6, x squared plus 12x. And then you take the second derivative, because concavity comes from the second derivative, and you get negative 12x plus 12. I'm going to set that equal to 0. So negative 12x equals negative 12, x equals 1. I'm going to do a sine graph of my second derivative. So negative 12x plus 12. It's because it's negative, it's going to go plus minus. And it's concave up, concave down. So f is concave up from negative infinity to 1 because f double prime is greater than 0. F is concave down from 1 to infinity because f double prime is less than 0. I'm going to stop this video. I'm not sure if I did that right. Hold on. What's going on there? Less than 0. I'm going to stop this video and we'll finish the last two pages of these notes on a separate video because it's fixing to be time for my next class.